Okay, so next. So 2 cos x plus 1. Nothing I can really do with that, but I can make that 1 minus cos squared x. Now I have myself a quadratic equation that has nothing but cosine in it. So from here, I have 2 cosine of x plus 1 minus 1. Those ones cancel. But when I go minus minus cos squared x, I get plus cos squared x equals 3. Now, how do you solve a quadratic equation? You move everything to one side and reorganize it so that the squareds first. And again, I think of this as just, a squared plus 2a minus 3 equals 0, and then I use my factoring skills. If my factoring skills fail me, I could always use the quadratic equation on it. And you never know. We actually did see one on a provincial exam once where it didn't factor. You had to use the quadratic equation and then your calculator from there. So let's see. Does this one factor? Yeah, this one does. What two numbers times to make negative 3 but add to make positive 2? That would be plus 3 and minus 1, right? So this is cosine of x plus 3 and cosine of x minus 1. Now, that would mean that one of my solutions is the cosine of x is negative 3, and the other of my solutions is the cosine of x is 1, and one of those things is not like the other. What can I do with the cosine of x equals negative 3? Nothing. That doesn't exist, right? Cosine can't be smaller than negative 1. So that one has no solution. The only solutions I have are when cosine of x is 1, and of course be mindful of your interval. Your interval tells us two things. It tells us A, we're in radians because it wants to 2 pi, and B, don't keep counting after you find answers between 0 and 2 pi. You just stop between there and there. So between 0 and 2 pi, when is cosine 1? Cosine is 1 at 0 and at 2 pi, right? So that's it. That's my two answers. X is 0 and 2 pi. And always be careful that if this was a curved bracket on either side, then that answer wouldn't exist, right? So that's it. That's the first one. For the second one, okay, they want this one in degrees. And what can I do with this? Well, cos squared, how about we change cotangent into cos over sine? And, well, that helps. And the signs cancel. That's nice. So now I have cos squared x equals cosine of x. The smart way to do this is to do the same thing I did on the first example. It's a quadratic. Move everything to one side, and then see if I can factor it. And I can. I can factor out a cosine of x. And, okay, so that means I have two answers. The cosine of x is 0, and the cosine of x is 1. When is the cosine of x 0? Between 0 and 360. That happens at 90 degrees and 270 degrees, right? X is 0 at 270. So there's two answers. And when is the cosine of x1? We just did that. At 0 and 360. So 4 answers for that one. Any questions on how I did those? Be prepared for ones that don't factor, where you might have to use your quadratic formula, or ones that are in, say, secant or something, so that your your equation's in secant, so that your final answer is the reciprocal, which means that, for example, had this been secant of x equals negative 3, then the cosine of x would be negative 1/3, and that exists, that has answers. But you'd need a calculator, right? So if I ask you one like that, it'd be on a calculator question. Okay, before we move on to other things, it's Q&A time. Guys at home, you get to play too. Does anybody have anything from any of the homework, 2.6.2, 6.3, 6.4, now that you've hopefully had some time to work on 6.4, where you couldn't get the same answer as the back, where you got stuck, or anything? Open forum for Q&A, and that could even include the review at the end of the note booklets. or the extra review that I handed you now. Is there anything you wanted to ask about? Can you go back down to question 2? My video glitched out. Yes, I can. Here, maybe make that a little smaller. There. Okay. While you're looking at that, people are rifling through their notebooks looking for things that they didn't know how to do. Okay, so back in the notes package. Okay, okay, you good there, Lucas? Okay. Oh, I'm saying people's names and we're recording. Sorry about that. Okay, so I'm going to go to the notes package. Notes package. And what page are we looking at?
Page 10.
So back. So page 15. You know what? Why am I doing this? I've only been using this technology for months. There, you can go scroll back much faster if you shrink it. So page 10, this guy, right? I don't want that, I want it bigger. There we go. Okay, so number 6 on here? Okay, so number 6, we would like to see if we could solve or prove that one. All right. Boy, that one's kind of like what's simpler, the left or the right? I think tangent to me is I'm going to leave tangent as tangent, and I'm going to play with the left-hand side. Did you do that? Which side did you pick?
I think I picked the left, yeah.
Okay, I'm going to pick the left-hand side. So I'm going to go to my identities for secant, cosecant, and tangent. If I scroll back just a couple of pages, I think, right? Oh, maybe a few more pages. Back to, no. Right there. So there's the two things I'm going to use. I'm going to use these two guys right here. So secant is tan squared plus 1, and cosecant is cotangent squared plus 1. So I'm going to use those two. Is that what you did?
No.
Well, there you go. If you change them both to sine and cosine, you probably did way more work than you had to, because those very quickly just turn into, okay, now where were we? There we go. So for number 6, I would just say, okay, so secant squared minus cosecant squared. And okay, so secant squared is 1 plus tan squared minus, and cosecant is 1 plus cotangent squared x. And look at that, you get to the right answer right away, because 1 minus 1 cancels, and then you have tan squared x minus cotan squared x, which equals the right-hand side. Is there a way to do this proof if you'd have switched everything to sines and coses? Oh, probably, but that seems to get me there much, much faster. Okay. All right. Anybody got anything from anywhere else? No? All right. I'll ask again tomorrow, and you guys at home you'll be at home tomorrow, you can play. And guys at home, if you're working on stuff tonight and something goes awry, you can bring it in tomorrow. But I do want to kind of get started on the next unit. It's a nice break from all the trig. And okay, so I'm going to go to here and go to here and there. Can everybody find that book? Guys in the room, you got it handed to you today. It should be the top of the pile. And guys at home, you had it handed to you yesterday. Okay, I'm just going to pause this for a quick second. Oh, there we go. Pause. We're back. Took me a while to find the file I was looking for. There it is. This is a classic problem in math. I think this is from a book printed in the 1950s. So, for those of you who can't see it from where you're sitting, I'll read it with you. Al's allowance. Al wanted his father to give him an allowance of $1 a week. Again, this is the 1950s. That was a lot of money back then. But his father refused to go higher than 50 cents. After they had argued about it for a while, Al, who was pretty smart in arithmetic, said, "Tell you what, Dad, suppose we do it this way. Today is the first day of April. You give me a penny today. Tomorrow, give me 2 pennies. The day after tomorrow, give me 4 pennies. Each day, give me twice as many pennies as you did the day before." "For how long?" asked Dad, looking wary. "Just for the month of April," said Al. "Then I won't ask you for any more money for the rest of my life." "Okay," Dad said quickly, "it's a deal. Which of the following figures do you think comes the closest to the amount of money that Dad will have to pay Al during the month of April?" So, are we looking at $1, $10, $100, $1,000, $10,000, $100,000, $1 million, or $10 million? Feel free to start calculating. I'll give you a minute. So basically, do you understand the proposition here? Al says, give me a penny on April 1st. On April 2nd, give me 2 pennies, because that's twice as much as the day before. On April 3rd, give me 4 pennies. On the next day, give me 8 pennies. On the next day, give me 16 pennies. Do you guys remember what a penny is? There was a time when we had a coin that was worth 1 cent. Yeah, it's been gone for a few years, but Dad in this problem would not go above 50 cents. And then he agrees to this scheme. So what do you think? Any ideas? Some people are punching buttons. Good plan. But there's got to be a systematic way to come up with this answer. So anybody got any guesses? Suppose I take. Hang on, let me take a screen cap here. The greatest thing Microsoft ever invented, the snip tool. Copy that, and then we can go to our OneNote page, and I'll just add a scrap page. There we go, and then we'll just put it there. There we go, Al's allowance. Okay, so why don't we call this A, B, C, D, E, F, G, and H? Anybody want to hazard a guess? What do you think? Somebody's right away saying H, which is not very much a counterintuitive answer. Here's how it works, and you're right, it is H. And here's how it works. If we say, we'll make a chart here. On day 1, payments, and then let's keep a running total for the month. On day 1, he gets paid 1 cent, right? And so he has a total of 1 cent. On day 2, he gets 2 cents, which gives him a total of 3 cents. On day 3, he gets 4 cents, so he's up to 7. On day 4, he gets 8, which is going to give him 15. On day 5, he gets 16 cents, which gives him 31. On day 6, he gets 32 cents, which gives him 63. And on day 7, he gets paid a grand total of 64 cents, which gives him $1.27. Are you sure you want to get to 10 million here? We're a week into the month. There's only 4 weeks, you know. And he's only getting $1.27 so far. This looks like a real good deal for Dad right now. It's going to turn on him real fast. In fact, if you kind of keep going with this, it starts turning kind of right away. 8 is now 128, so we are now at 255 cents, or $2.55. And then it starts kind of ballooning really quick after that. Let's go to kind of the math of this. If this is X, give me some sort of expression for this number. Any ideas? X times 2? 2 times 1 is not 1. Now you're saying, somebody kept saying doubling, right? Yeah, you're doubling, but like this is 2 times 1, this is 2 times 2, this is 2 times 4. plus x times 2. So if x is 4, 4 times 2 is 8. If 5 times 2 is not 16, no. 6 times 2 is not 32. No, it's a little more complicated than that. You know, the big hint would be, what's the name of the chapter we're about to start? Yeah, there's exponents involved here. In fact, this number here is 2 to the power of x minus 1. Right? Because this is 2 to the 0, this is 2 to the 1, this is 2 to the 2, this is 2 to the 3, this is 2 to the 4, this is 2 to the 5. You get the idea. And then, if you really want to notice, do you guys notice a relationship between the numbers in this column and the numbers in that column? It's the previous number minus 1. Here's 127, that's 128. Here's 255 because this is 256. So in other words, this number here is 2 to the 8 minus 1. Well, that number there is 2 to the 9 minus 1 minus 1. So this is, you could say that this is 2 to the x minus 1. Get it? Do you see how the minus 1's different there, though? This one is part of the exponent there. It's just the answer. So that actually will give us our answer. 2 to the x minus 1. I just have to figure out what x is. How many days are there in April? 30 days, September, April, June. So it's got 30. If I don't do the little song, I don't remember. It's 30. So 30 goes in to here and here. So on April 30th, I'm going to need a calculator for that. 2 to the power of 30 minus 1. On April 30th, now remember this is in cents, so I'm going to divide it by 100. On April the, oh hang on, I just did that wrong. 2 to the power of 12, sorry, I want to do this one. Yeah, so on April 30th, the payment on April the 30th is 2 to the 29. So 2 to the power of 29 is, and again, divide that by 100 because that's in pennies, $5,368,709.12. And that's just how much he got paid that day. The running total for the month is 2 to the 30 minus 1. So it's basically double this number and then minus 1. So that's what I'll do. I'll just times it by 2 and minus 1. Oh, wait a minute. Minus 0.01 because I put it into cents. So it's going to be $10,737,418.23. So there we go. And that's the way the numbers take off on you when you're dealing with that kind of math. That's L's allowance. And a similar story, and my apologies to anybody in the class here who is actually of Indian descent, and I am butchering a cherished fable from your culture, but I'm going to do my best here. It's called The Legend of Palpatine, and basically it's about a king who is a big chess enthusiast. He has the habit of challenging wise visitors to a game of chess, and one day a traveling sage, he didn't notice the guy was blue, but okay, a traveling sage was challenged by the king. To motivate his opponent, the king offered any reward that the sage could name. The sage modestly asked for just a few grains of rice in the following manner. The king was to put a single grain of rice on the first chess square. Have you heard this story before? Then 2 grains of rice on the second square. Then 4 grains of rice. Each square along the chessboard, doubling how many grains of rice were on the previous one. So, having lost the game and being a man of his word, the king ordered a bag of rice to be brought to the chessboard. Then he started placing rice grains according to the arrangement. 1, then 2, then 4, then 8, and so on. And of course, the numbers go crazy big. G, of course, stands for billion, right? You don't even make it halfway to the board, and you already have to try to stack 512 million grains of rice onto one of the squares. Following the exponential growth of the rice payment, the king quickly realized that he was unable to fulfill his promise because on the 20th square, that's 1 million grains. On the 40th square, we're looking at 1 billion grains. And finally, on the 64th square, I have no idea how to read that number, 18 billion trillion, if I got that right, grains of rice, which is about 210 billion tons. Somebody actually did the math on this, and is allegedly sufficient to cover the entire territory of India, a meter thick in rice grains. At 10 grains of rice per square inch, the above amount requires rice fields covering twice the surface of the earth, and that includes the oceans, where apparently you can't grow rice. It was at that point that the visitor, the sage, revealed himself to be Lord Krishna, who apparently that was one of his things. He would just wander around in disguise to nobody noticed he was blue again. He revealed his true identity to the king and told him that he doesn't have to pay the debt immediately, but can do so over time. And apparently this led to the tradition of visiting pilgrims still feasting on palpatine, which apparently is like a rice pudding kind of a dish, I'm told. And that is the king's debt to Lord Krishna still being repaid. So I always like that story. I think it's a cute little story. And I have a link to an actual animation of this story on my blog that was made by IBM in the 1960s. IBM used to be very much in the education business back before they ruled the world. So anyway, that's the Legend of Palpatine, and of course Al's allowance. Another version of the same story is, of course, you can prove that there's no such thing as vampires using exponents, because again, let's assume the first vampire came along when Bram Stoker wrote the famous book Dracula, which was in the 1880 roughly. I think it was in the 1870s, but let's say it was 1880. So let's say in 1880 you've got one guy, Count Dracula, and let's say that he has to feed at least once a week or he'll die, which is pretty much the same for us, right? And let's say that he is, of course, going to not kill his victims. He's just going to bite them, which of course turns them into vampires. So that means after 1 week, there is now 2 vampires. And of course, those vampires have to feed. So after another week, there's then 4 vampires. And so basically, the total number of vampires ends up being 2 to the x minus 1. How long does it take that to become, what's the population of the Earth right now? 7.5 billion? That's 700, that's million only. There we go, that's billion, right? 7.5 thousand million billion. How long would it take? What's x? How many weeks are we looking at? Now we realize we've hit a bit of a problem. If I were to approach this the way I approach kind of ordinary algebra, I'd have to add 1 to both sides of the equation, right? Which, very nice. There. Now, how do I solve for that x? Well, I can guess and check it. Right, let's see. 2 to what power gets me closest to 7.5 billion? So 2 to the power of, let's try 100. Way too big. I got a number that's in scientific notation. It's a 1 with then 30 more digits on it. So 2 to the power of, let's cut that in half, 50? Still way too big. 15 zeros. So 27? So there you go. So it only took 27 weeks before the entire population of the Earth, and of course in the 1800s there was nowhere near 7 billion people in the world, but if there had been, it only took 27 weeks. Oh, you were guessing? Oh, I thought you'd actually done the math. Okay, let's see. 2 to the power of 27. That's not too bad, actually. That's this number. 2 to the 27 is 134217728. So comma. I know you're not supposed to use commas; it offends the French, but whatever. You're supposed to use spaces nowadays. So let's see. That's not as big as that, but times it by 2. That's 28. Times it by 2 again, and I've hit 5. 3, 6, 8, 7, 0, 9. Oh no, I'm not. Actually, no, I'm not. I'm not quite close enough. I'm a place value off. So I'm going to go. No good. I'm going to try 2 to the 40. 2 to the 40. There we go. That's 1099511 628. So that's 2 to the 40. So times that by 2, 41. Times it by 2, 40, and then times it by 2 again, so 43. So at 43 weeks, I passed this number because I hit 8 billion. So there you go. It only took 43 weeks. So either there's no such thing as vampires, or we're all vampires, but we're in denial. There's no other explanation. Or it's like Twilight, and we just got the sparkly romantic vampires that feed on rats and stuff to spare us humans. Aren't they nice? Okay, so there you go. There's my introduction to exponentiation. Let's go to the notes. And I've actually kind of split up the notes. Oh, I'm already on the notes. There we go. There. There we go. I've kind of split up the notes. We're actually going to start with what's actually in your textbook, chapter 7.3. We're going to do the graphing separately. We're going to just focus on the arithmetic and the algebra for now. So before we do anything, do you remember grade 9? That's where we got to start. Oh, good, yeah. Just saw a wave of PTSD wash over the room. Grade 9 exponent rules. What happens when you multiply two powers that have the same base? What do you do with their exponents? You add them. So this is x to the 7. If you take the power of a power, the exponent of an exponent, what do you do with those? You multiply those. If you divide two exponents with the same power, careful, I'm going to get all kinds of people who think that's x to the 5. You subtract. That one's x to the 12. Any number that is not, notice we did say at the beginning that x and y aren't 0. Any number that is not 0 taken to the exponent 0 is 1. Yeah, make sure that you do understand 0 to the power of 0 does not exist. You can't define what 0 to the power of 0 is. Okay? Everything else, every other number in the whole universe to the power of 0 is 1. When you take an exponent of a product, you can distribute that exponent. That's called power of a product law. And it works the same for quotients. You can distribute an exponent through a quotient. Make sure you understand that what you can't do is distribute an exponent through a sum. Those two things are not equal, right? You cannot do that. And it should make sense when you think about it, right? An exponent is repeated multiplying, and multiplying is repeated adding. So you've kind of jumped past a level if you think you can go from here to here. You do know that to square this thing, of course, you get a middle term that is missing from here. So you can't do that. Okay, good. So as long as we understand that. Now, do you remember what fractional exponents do? They, of course, give you radicals. And this one, I like this one. You know, this one you can actually think of a bunch of ways. I'm gonna write this one a few ways here. I should have more room. You can think of this as x to the 1/3 squared, right? Because when you multiply a third times 2. And you can multiply things in any order. So it would be just as correct to think of this as x squared to the 1/3. And that means that you can think of this as the cube root of x squared, or you can think of it as the cube root of x squared. It does not matter what order you consider those two things. Let me make that bigger. All of those things equal the same thing. And maybe a better way to write this, you could write this off to the side if you need a refresher, is x to the 1/a is equal to the eighth root of x. Right? That's the rule. Fractional exponents make radicals. A square root means power of a half. You learned that for the first time in grade 10. And what do negative exponents do? Do you remember what they do? They make reciprocals. So again, if you want that as a rule, x to the power of negative a is 1/x to the positive a. So those two rules there are the two that some teachers do them in grade 9. Certainly when I had an honors group, I made sure that we did this with grade 9. And even if I had just a regular class of grade 9s that was a little on the stronger side, we'd get to that. But it's actually not in the curriculum that you have to know these two things till grade 10. So that's grade 10 exponent laws. All the other exponent laws you did in grade 9, those last two are grade 10. Okay? So there's, oh wait, sorry, somebody had a comment about Dracula. Or the ones after Dracula don't need to feed like Dracula. Yeah, okay, but I'm going to say that no, if you're a vampire, you got to eat. Man's got to eat, vampires got to eat. So there you go. My exponent argument holds, I think. Now, some of the next couple of tests, the chapter 7, 8 test, will be with calculator, but a lot of it will be without. You're expected to know some common exponents. I would say you should know your squares. You should know x squared for x is between 1 to 20. So I'm going to just jot that down. And that was true in grade 8. The curriculum says up to 15, but come on, if you went to Acadia or Leach, I'm sure your teacher went up to 20. So quick, what's 19 squared? People are like, that's no fair, that's not in the times table chart. If it wasn't on that poster in the wall in grade 3, I don't know it. Right, the bottom corner was 144. So 12 squared is 144. What's 13 squared? 169, 14. You just have to flip those digits on the last two. 196. Starting to come back to you now. 15 squared, 225. And that's where the curriculum says in grade 8 you're supposed to know. But 16 is 256. 17 is 289. 18 is 324. 19 is 361. And of course, 20 squared is 400. Okay, so you should know those. Then, of course, you should know all of these. See how many of them you could just jot down. Go. Without touching your calculator. Here, I'll make that once. I hope people at home aren't looking on their phone. It's going to be some small looking work here. All right, let me see if I can catch up to you. There we go. That should be pretty easy. You're just doubling things. Anybody play that game on their iPad or the 2056 game where you move boxes around? Yeah, you get familiar with these numbers real fast if you play that thing. But how's your threes? You good? And of course, your fours are already in your 2 column if you think about it. You just have to kind of think 4 squared. If you'd like, you can just say, well, yeah, 16 and 4 to the power of 3 is the same as 2 to the power of 6, so 64. And 4 to the power of 4 is the same as 2 to the power of 8, which is 256. Because think about it, 4 to the power of 4 is 2 squared to the power of 4, which is 2 to the power of 8, right? The games you can play with exponents. And then, of course, your fives. If you know your first 4 fives, we're happy. And if you know your first 4 sixes, we're happy. 6, 36, 216. And then I believe it's, what is it? It's, oh, I should know this one. 1296, that's what it is, 1296. Yeah, there we go. Okay. So, there's where you should know. Some other things about exponents that should not be news to you. Let me make the screen bigger here. There we go. If c to the x equals c to the y, then x must equal to y. For example, if I have a nice little equation like 3 to the power of x plus 2 equals 3 to the power of 7, then I know x plus 2 must equal 7, so x must equal 5. So let's solve an equation like that. I know 2 to the x plus 1 is equal to 32. That's my equation. I'm solving for x. So I'm going to say that 32 is 2 to the 5, because I know that from my memorized chart on the last page. And then I can say that x plus 1 equals 5. and then x is equal to 4. Now, I want to show you how to lose half a mark on this. If you were showing your work like this, students do this all the time, and when we're marking provincial exams, they tell us this costs a half a mark because it's a mistake. It's bad communication and bad logic, and it's wrong. Students will say, oh, the 2's cancel, and I have x plus 1 equals 5. Now, I want you to think about why I have to call that wrong. Obviously, you're going to get the right answer. You're going to get x equals 4. Why am I hassling you when you got the right answer? Because you're not thinking properly. You see, canceling 2's means that you divided both sides of the equation by 2. And that's clearly not what happened here, right? You can't say 2 to the power of x plus 1 divided by 2 is x plus 1, because it isn't. In fact, you know what it would be? What would this equal? It would equal that. Do you see why? Because this is 2 to the power of 1, right? And what do you do with exponents when you're dividing? You subtract, right? So saying that you canceled these 2's and then continued on with the same equation is in fact false. What you did, in fact, this is how I tend to show my work when I'm doing these. I put a therefore, because this equals this, therefore I can make up this brand new equation. Starting here, I made up a new equation, right? Because this thing equals this thing, x plus 1 has to equal 5. This is not a continuation of that equation. I've taken this equation as far as I can. I'm starting on a new one. Does the logic of that make sense? If we see this in your work, they tell us, take off half a mark. That's a kid who isn't thinking right and wasn't taught right. Everyone should understand that this equation here died right there. I had to start a new equation to solve for x. So keeping that in mind, that's the way we're going to move forward. So this is 3 to the power of 4x minus 1. And 27 is 3 cubed, but I'm taking that to the power of 2x. So my new equation is 4x minus 1 has to equal 3 times 2x. So now let's see what we can do with that. That would be 4x minus 1 is equal to 6x. I'm going to minus 4x from both sides. And then x is equal to negative 1/2. And by the way, just like all algebra, when you're doing algebra with exponents, you can do checks. If I plug negative 1/2 in where that x is, I should get a true statement. Let's see if I do. That by the way, is a half. Sorry, I'm writing too small. I'm looking oogly. So this would be, let's see, what is 4 times negative 1/2? That would be negative 2 minus 1, so that's 3 to the negative 3 equals 27 to the negative 1/2. And again, what do my rules tell me? They tell me that, let's see, what is this? This is negative 3. So 3 to the negative 3 is 1 over 3 to the 3, which is 1/27th. And this is going wrong. Something is wrong here. Oh, I forgot the 2. That's why. Oh, okay, sorry. Hold on. Hold on. Look at this. I misread the question. Checks only work if you actually copy the equation right. There we go. So 2 times negative 1/2 is negative 1, which is 1 over 27. And there we go. Left side equals right side. True. That is a true statement. Okay? Let's try another one. What are you thinking when you look at that? Hopefully you're thinking, let's get everything to a base of 3. This one's already a base of 3. 27 is 3 cubed. And 81 is 3 to the power of 4. Then I'm going to get this into one base. When you multiply two powers that have the same base, what do you do with those powers? You add them. And I might as well take this as a power of a power. So that's 4 times 2x minus 1. And now, once again, I can use my therefore. If this base to this power equals the same base to that power, then those two powers have to equal each other. And then from there I can just solve this algebraically. So that's x plus 3 equals 8x minus 4. Negative 7x is equal to negative 7, and x is equal to 1. You can do a verify if you want, but obviously 3 times 27 is 81. You can kind of see it visually. All right. Now let's get some radicals involved. Once again, what should you be thinking? You should be thinking 4 can be expressed as a base of 2. So 4 is 2 squared. But that's 2 squared to the x plus 1. 2 to the x. And let's get rid of the radical and change it to a number I can work with, a fraction, right? Because that's what square root of 2 is. It's 2 to the power of a half. On the left side, power of a power means you multiply the exponents. And on the right side, you add the exponents. And once again, I can use a therefore. 2 times x plus 1 has to equal x plus 1/2. And so that's 2x plus 2 is equal to x plus 1/2. I minus x from both sides. I minus 2 from both sides. No, I don't want decimals. 2 is 4 halves, right? So x is negative 3 halves. And you could do a check on that if you wanted. It would work. Okay, what am I going to do with example 5? Well, remember that I had a rule that we looked at a few minutes ago that said x to the negative a is equal 1 over x to the a, right? That's how negative powers work. So if I have 1 over 3 to some power, that's like saying 3 to the negative of that power. And while I'm at it, 81 is 3 to the 4. See how that works? So negative x minus 1 is equal to 4. And so negative x plus 1 equals 4, and x is equal to 3. Oh, negative 3, sorry. I lost the negative. X is equal to negative 3, thank you. Okay. Next, what do we want to do with example 6? Well, what are you thinking? What would be the common base of all of those factors? They're all powers of 2. 8 is 2 cubed, and I'm taking that to the power of 5/3. Remember that this negative is, of course, not part of the base. Do we have to have that conversation? Chances are we should all understand this, right? Those two things are not the same number, right? We good with that? This is like saying I want negative 2 times negative 2. That negative is part of the base. That's 4. But this is the negative of 2 times 2. That's negative 4. Right? So back over here, that negative is not part of the base. That's why I didn't include it in the bracket. He can't come in. Over here, that's 2 times 2 squared to the x over 2. All right, what can we do with this? Well, power of a power means I'm multiplying. 3 times 5/3 is just 2 to the 5. And over here, I have 2 to the 1 times 2 to the x. And I could say that this is like saying the negative of 2 to the 5 is equal to 2 to the x plus 1. Does everybody get how this became that? Because remember, 2 means 2 to the power of 1. And what do you do with those two exponents? You add them. Okay, so if that makes sense to you, where do we go from here? Can we make a therefore statement and move on and say 5 is equal to x plus 1? This one doesn't have a solution. How come? Because how could I possibly make the right side equal the left side? What number could you possibly put in for x that would make this turn out to be a negative value? Right, because this side's negative 32, right? No solution. Why? No value of x could make the right-hand side negative. There's people going, well, what if you put in like a negative number for x? Try it. Does negative exponents make negative numbers? No, it just makes reciprocals. If the base isn't negative to begin with, there's no way to get a negative number. So we wanted to have one in there just to make sure that made sense to you. That doesn't solve. There is no number in the universe that you could put in for x that would make that a true statement. Okay, notice we cannot yet solve for things that have different bases. That's coming up in chapter 8. Speaking of which, that's actually the only part of chapter 7 we're going to do now. So 7.3 is it for chapter 7 for now. And I put on the blog here. Here, let me show you what the blog says. The blog says, no, that's not where I want. There we go, that's where I want. The blog says, you're not slot 2. The blog says we did the ACC for 6.4, and then we asked if anybody was stuck on anything in chapter 6. We'll ask again tomorrow. Then we did the 7.3 lesson, and I'm recording this. I guess I can stop now.